Okay, so let's move on to the third session in this second unit of operating system. So in this particular session, what we are trying to understand is the task or process, the basic concept of task or basic concept of process and its management services. And after this particular session, one would be able to understand what is task management service of an operating system and how operating system manages this particular service with all its allied data structure and the different variables that is being used for making use of this particular task management service. So what we are going to discuss in specific in the today's session is all about what is the process of or what is the concept of process, what is the task or process state diagram, the data structure upon which the scheduler works in order to manage the task or manage the process. That data structure is called as a process control structure, that's called PCB, or task control block called as an TCB. What is exactly mean by a process switch? As a procedure, how does the process switch would take place? And what are the different scheduling policies that one would need to understand and the process operation? I repeat, these particular concepts which are being there into this operating system, these concepts are fairly general concepts. Okay, we will try and understand these concepts from the purview of understanding the real-time operating system, which will be our next units. So we are going to understand this particular operating system in nutshell for as a basics of the different processes, or the basics of different process management, the context switch, scheduling mechanism, and what are the different operations that happens to be on the process. In MUCOS 2, which is the study of interest, so that particular MUCOS 2 makes use of the word called as a task instead of process. Okay, rest of the philosophy or rest of the working operation on this would definitely be the same one as you can expect and you can really understand. Okay, so let's try or let's start discussing about the basic concept called as a process. Okay, this complete slides I have taken it from the book that I already referred the last time called as a Galvin book. So Silsbers, Galvin and Gange, they are the authors of this particular book, and they have provided the PowerPoint presentations also on the content of this particular book. So I'm straight away taking the PowerPoint presentation, which is being available even on the internet for which is being given by the author called Galvin. Okay, and this is what like the book reference that we are referring, that operating system concept 9th edition of this particular Galvin book. Okay, so let's understand what exactly the process is all about. Okay, so when operating system executes variety of programs, these programs are either getting categorized into a jobs or user programs. Okay, and jobs are basically referred to as in system programs, or that's called as a batch system. And whenever we are making use of this particular different programs, users specifically users program, then these user programs are basically there in a time shared systems, and these time shared systems which is being written as a user, those are specifically referred to be as a tasks. Okay, so user programs are referred to be as a task, and there are some processes or there are some entities which are being used by an operating system for various purposes. Those are getting referred to be as in processes. Okay, so processes can be internal to an operating system, as well processes can be an external, that is the user program of the operating system also. Okay, so that, or what exactly the process is all about. So it is being written that the process in the program in execution or the process execution must progress in sequential fashion. That means if I refine this particular definition of process or task from our purview, then this particular definition of process and task that gets to be as any self-sustained entity that can be executed is referred as a process or task. I repeat, any self-sustained entity or any self-sustained program that can be executed is referred as process or task. I'm saying self-sustained. That means whatever is being required in order to execute that particular program, if that requirement gets fulfilled, an operating system gets to know that this program or this particular process or this particular task can really be executed, then that portion of the execution is called as a process. As simple as that. Okay. Further, we'll see that there happens to be a difference between this process and thread. Okay. So thread are also a tiny executable program, which is again a self-sustained, which operating system gets to know about its existence. And how does operating system get to know about its existence? That we are going to see through the different data structure that operating system makes use in order to make use of this particular process for different operations. And that is what the concept of process, as simple as any executable entity or any self-sustained program that could be understood by an operating system for an execution, is called as either a process or a thread or a task, anything, because that can be used as an interchangeably. That's what it is being written. Like even this particular textbook also uses the term job and process in most interchangeable fashion. Okay, it's completely depends on what kind of application or what is the operating system is being used for. In the last session, we have seen that the different actors would see this operating systems into the different role of it. Okay, and that is what the beauty of this operating system understanding, that the purpose for which I am supposed to make use of it, I am supposed to understand the operating system concepts or operating system internals from that particular purview. Okay, so that is what we also discussed in the last session also. Okay, so when we say it's a process, it comes with multiple parts of it. When I'm saying it's a self-sustained process, okay, so this process has to, whenever it is an execution part, whenever it's a program in execution, that has to be resided into the memory, isn't it? So whatever the structure or whatever the information related to that execution part, that information is stored somewhere into the memory, and that information is getting used by the scheduler in order to understand the different attributes of this particular process. By virtue of understanding these attributes of the process, the scheduler will be capable to schedule that particular process or task as per the scheduling policy that is being written by in the operating system. Getting my point? So that is what it is being said, that this data structure, which is being used in order to control the operations on a processes, that particular data structure is called as a process control block or task control block in short. Okay. So what are the different multiple parts that it is being there? See, the program code is also called as a text section. In the book, it is being written that there are some entities which is being holding into the operating, into this particular data structure or in a memory, which operating system scheduler makes use of in order to make some certain operations, in order to control the operations on this particular executable portion of the program. That is what we call process or task. Okay. So the first point or the first part that is being narrated into this particular a book, which is being given as it's a program code itself, that is called the text section of it. Then current activity, including the program counter and process register. Okay, whenever we are saying it's in process management, task management, we should not forget anyway the process called as context switching, because this context switching is a de facto or internal process by virtue of which the task management would be possible. Otherwise, that task management would not be possible. So directly the program counter and different processor registers. What is the role of program counter? As we know, program counter is basically used in order to keep the track of an execution of an application or track of execution of the program. The processor registers, we understand that everything and anything that is required to be executed into the processor takes the help or need the help of the structural resource called as a processor register. Like even last time also I told you one very simple example. Even if you write like C is equal to A plus B, then whatever the variables that we are writing in the program from the user's perspective, these variables are expected to be actually stored or lodged into some of the processor register. And these registers would be given to the ALU, or these registers are being there used by the ALU by the command that you are writing it, isn't it? And based on that, this particular processor registers are basically used for different arithmetic, logical, branching, any kind of operation. You need to have processor register. And that is what you came to know, very interesting word that is being given in the architecture of any processor or controller, that is called as a programming model, isn't it? So this particular programming model consists of all the general purpose registers and the different registers which are being there as a special function registers, which are basically used in order to control or in order to execute the program from the underlying hardware. And that is what we need to understand, that processor registers are extremely important entities which are expected to be pushed and popped from the stack whenever you come across the change of the process or change of the task by scheduler of an operating system. Okay, so the second entity that comes to be as an its current activity, including the program counter, because it keeps the track of execution. Okay, then we are in the context switches that we are supposed to understand it in more rigorous way. Okay, then the processor register, as I narrated at the moment, like there are different registers. More the number of registers onto the processor, better the context switches, or better the space, better the local memory, better the CPU register memory that could be available for storing and restoring the content to and from the those particular registers. And context switches happens to be a faster one. Stack, that is containing the temporary data, that's called as in function parameters, return addresses, local variables. As even we have seen this particular concept when we discussed the re-entrant function also, if you remember. So during that also we have discussed that if you are using some call functions and all that, if you are using some kind of multiprocessing, multitasking activities, then this stack maintains the context. The stack operation is to store and restore the context that is being required for the multiprocessing. In order to, the context itself is a word that is giving a meaning of what kind of references that we need to understand in between the process switches, task switches from one to another. And that's what it becomes very important, like sample context, which is the sample parameter as a context that is being given. As you might have the function parameters to be passed on, you might have the return addresses to be passed on, you might have the local variables to be passed on. Like for example, if at all you are using a function in task 1 and task 2, you are using the same function, you are calling the same function. Okay, but the difference is that you are passing different arguments, they are passing different parameters to that function in a task 1 and task 2 also. Okay, so what parameters you are passed, what parameters you have passed into the function that you have called in task 1 and task 2, shouldn't that be recorded separately somewhere? Else otherwise, when task 2 finishes its execution and task 1 regains control back for execution, how task 1 would understand that what is the parameter that is being passed into the function, if at all, that function, within the execution of that function, the multitasking has happened. Let's say that particular function has got 10 lines for execution, for example, and at the 5th line of it, by some virtue of multitasking event that we'll be seeing in detail, by virtue of some multitasking events, at the 6th line of that execution of the code for 10 line for that function, in the 6th line in between, the task switch has happened and it has to go for the task 2, where that task 2 calls the same function with the different parameter that is passed. Getting my point? So current context would be the current parameter that is being passed into the task 2. So when again the multitasking happens, when task T2 again no more be there in execution, task T1 will be there in execution, then what will be the scenario? The execution that would start from the function that is from line number 6 or 7, right? From where it has been left of execution. Then when it's executing, what all the parameters that it has passed as in function parameters, it should not take up the current value that it has been there from task 2. It has to take up the value from task 1 stack itself. That is what stack, which is being referred to as a private memory to every task, or private memory to every process, or private memory to every thread. Getting my point? And that ensures the reentrancy of the function, that ensures the correctness of the resources, even though you are using resources in a shared manner. Because you cannot expect that you would have the resources which are mapped as one-to-one. That is, so many number of tasks are there, so many functions are there, so many resources are there. That cannot be the case ever. You definitely might need to make use of those resources in a shared fashion. And when you're using resources in a shared fashion, the task management also has to take into account what kind of protective mechanism, what kind of mechanism would be incorporated into it, so that the integrity of the data relevant to that particular execution section within the task, that would be maintained. And whatever the corruption that might happen because of the shared data, that corruption definitely would not be there into the system. So when we are talking about this operating system, as it provides the services, it has to provide the services with 360-degree of its operations. And that is what we are trying to understand, insights of the insights of the task management service of this operating system. Okay, so as I was telling you, that stack that is containing the temporary data, which might require the function parameters to be passed on, return addresses and local variables that is being expected. Then data section that containing the global variables, and heap that is containing to the memory dynamically allotted during the runtime. This is more specifically when you are making use of operating system for the desktop. Okay, this particular book does not specify the operating system usage in any way. More specifically, this particular book enlightens us about the basic concepts of operating system in general, and more specifically general purpose operating system. Getting my point? And we are more into understanding the embedded operating system, but embedded operating system, as it is being derived from general purpose only with a specific application on a specific architecture. So we cannot say that the concepts are completely different. That is what this particular unit aims to understand, the basic concepts of operating system that we are further extending to the embedded operating system or real-time operating system, as simple as that. Okay, so even in most of the cases, we definitely does not encourage in embedded OS to make use of this particular heap service of operating system. Okay, because very few real-time operating system or very few embedded operating system would make use of dynamic memory management. Okay, so being lacked in dynamic memory management, we definitely does not expect any kind of heap service to be provided, if which is a dynamic memory management service to be provided for it. But as this particular context is being there with a general purpose operating system, so dynamic memory management is expected to be there, and that becomes some part into the different parts that the process would have with it. Okay, fine. So let's move ahead in understanding the further part of the process basic concepts. That this is very interestingly that is being written, that program is passive entity stored on the disk, that is executable file, where process is an active one. I think this particular line talks so many things onto it. That is what I said, that executable entity, self-sustained executable entity that can be scheduled by the scheduler of an operating system is referred to be as a process or task or thread. And that is what it is being written, that program which is being there into the memory, unless and until that particular program is not being referred or not being made references to the scheduler, that cannot be an executable one. An attempt of making your program into the memory, so to the scheduler referencing so that it can be executed, all these particular things that gets into the process kind of things. In the state of the process, we have one state that we'll see in this particular book. It's not being defined there, but there is one state that we call as a dormant state of a process. And that dormant state of a process is referred to be as a program, because it is passively residing into the memory where the scheduler does not get reference of that particular program into the memory. And that is what very interestingly it is being written, that program is passive entity stored on the disk while the process is an active one. Because program becomes process when executable file loaded into memory. And what that executable file is all about. That executable file is all about the references that the references that the memory section would give to the scheduler in order to get it executed. Okay, and what all that references are there, we are going to understand it from the task control block of it. Okay, so it's as simple as this. So execution of programs started via GUI, mouse, command line entry of its name and etc. One program can be a several processes. So consider multiple users executing the same program. That can be one of the example. Okay, I don't need to tell you in a different way, where when we do the activity of Control Alt Del, we get to know that for a running application, how many processes are being there. First of all, with the Control Alt Del, what operations we get to know? That is the task manager. When we invoke the task manager, we get to know how many tasks are being there into it. Then we are going one level down to that, which is a process level, right? Where we could get to know how many processes are being there into it. So many times it is being expected, especially for the operating system, that something when malfunction is going on, and when you refer the blocks of that malfunctions of operating system, many times it is being referred to kill the few processes, because that might be there in a corrupted state of it. Means the program would be converted into the processes, and processes further when multiple user wants to execute that particular process, it goes on to the thread level of it. So that's what you have: program, process, and then you have got threads. I request you to do this particular exercise today itself. Whatever you are running into on your systems, just make Control Alt Del and just try and understand the hierarchy between this. You have got some kind of x number of tasks, you have got n x number of processes, and you might have n factorial x number of threads which are being running onto it. So that is the level of, and every process, every thread has to be, hierarchically connected, hierarchically linked through some IDs, which becomes the task ID, process ID, and thread ID. And that is what the beauty of this particular data structure that we are referring to be as an process control block or thread control block. Okay, which we'll try and understand it very soon now. As I said you that these are the few sections which are being there into memory: text section, data section, heap section, and stack sections. Okay, so this is the mapping in the memory where the different attributes of the process or different attributes of the task would resides into this particular memory. Fine. And going ahead, like we'll now understand what are the state of the process. Okay, so this particular process or this particular states of the process that happens to be as we can have the different states of the processes, and these states of the processes happens to be, you can have a state called a new when the process is being created. You can have a state of a process called running when instructions are being executed or that particular process is being executed, or you can have it within waiting where process is waiting for some events to occur, or you can have the state called as an ready where you can have that the process is waiting to be assigned to the processor. That means whatever is being required to execute by that particular process or task, everything is being there with the process or task. Only the thing is that it is not being scheduled to the processor in order to get it executed. That is what, when something is being there already acquired every requirement, but not getting executed still by that point. So that is what referred to be as a ready state of the process or ready state of the task. Okay. And then when you finish up that process, it's called as a terminated state. So these states resembles to the very own states that we are supposed to understand into the MUCOS2. Okay. So let's see this particular transition of this particular states again. Okay. So transition of the state happens to be in this way. For example, you please mark the direction of the arrow. You please see the direction of the arrow very carefully. Okay. So you can see that when the process is being created newly, or when task is being created newly, it resides into the memory. Okay. So that is what we call as a new process or new thread is being there. Okay. So unless and until that is not being referenced, okay, after that it might be admitted to the ready state. Means whatever it is required, everything is being fulfilled for that. So it is there in a ready state. And after which this particular ready state would be migrated or transited to the running state, provided the scheduling algorithm would allow to change the state from ready to running, or scheduling algorithm would allow that particular task or process to be running one. And that is what we say, that the transition happens to be ready to running. There are different scheduling algorithms that we already know it, right? Or the very simplest algorithm that I can get to know is round robin algorithms, where time slicing is being provided with a fixed priority. So based on the time slicing and fixed priority, the task would migrate for its execution by the scheduler. So when one task goes, or one process goes from one to other state, when the process is being running, for example, process 1 is running and process 2 is ready. The process 1 has elapsed its time period, which is being allotted for it. So after that, process 1 has to be preempted, or process 1 has to be put into the wait state till that particular process turn that comes out. Then what is the next process according to the priority and according to the time slices? The second process, process 2. So process 2, which is being there in a ready state, that would be put into the running one. Unless and until the process or state or process or the task is not being there in a ready state, it cannot be there into the running state. Unless and until, I repeat, unless and until the process or task is not being there in a ready state, it cannot be there in a running state. That is what, if you carefully observe, there is only one transition arrow that goes from ready to running, or to the input part of the running, you have got only one transition. And that transition is always from ready to running. And that is what it is being said, that the task which is ready to run would always be running. The task which is being there in a waiting state or newly created, that will not be at all in a phase of running unless it goes on to the ready state. That is what the TCB or task control block is always being there, with a different supplementary kind of list called as an ready list. Whatever the tasks which are being there in a ready state, those tasks are being there in that particular list according to the priority, and based on the scheduling algorithm, this particular task would be, which are ready one, would be taken for the execution, and that would be there into the running state. Okay, so this transition is very interesting and important, that ready to running transition. Now when task is running, what are the different activities by which that running task would be preempted, or running task will no longer be in a running state? The different activities which is being given is, once that particular task finished its execution and it has been given with an exit mode of operation, and that is what you have got. The very first thing is that when it's running, it can be terminated. Okay, when it's running, it can be terminated by the exit path of it, or when it is being running, it can be again put into the ready state, if the interrupt has occurred. When task is running, some interrupt has occurred, and that happens to be a high priority interrupt. Then we understand that when high priority interrupt occurs, the current task has to get preempted. Current task, the interrupt service routine is to be executed. So in that particular process, you can have the state of this particular state would be transited from running to ready state because of the interrupt one. Why it would not go into waiting one? Because it is not waited for anything. It is being preempted because of the interrupt arrival. Because of the interrupt arrival, it is being put into the ready state. Okay. The next transition that you can see, that from running to waiting, and this is very, interesting transitions. Okay. So task is running, and in the program itself, let's say that you have made some provision in the program that task would no longer be continued unless it comes out to the expectation, or unless it meets some kind of requirements. Unless it makes some kind of requirements, this particular task will not be there further running onto it. So even though task is running, even the process is running, when the task is running and you made in between that task some conditional statements, and if that condition is true, only in that case, only that case you can have the further execution of the program. Okay, but you can see that, or for an example, let's say in an application or in a task, you have written one variable, okay, and that variable is checked or you are checking that variable on a condition whether that variable become one or zero, and that depending depending on the arrival of some event, you are making the state, or you are making that variable to be changed from 0 to 1. And once that event occurred, when the variable changed from 0 to 1, only in that case the further execution is to be go on. If what does it indicates? The running process or running task is waiting for some event, isn't it? A running task is waiting for that event. Is that task is ready to run? No. That particular task would be from running, it would be put into the waiting state. And whatever for which that particular task has waited, once that is being met, it would be put into the ready state. Why it cannot be directly in a running state? Because till that, at that particular time, the other tasks are running. That is what the transition even from waiting to running is not possible, because unless the task is not ready, it cannot be run. That is what the reason, again, you can have the further transition from waiting to ready state of it. That is what when task is running, when task is waiting for some event to happen. So if that event doesn't happen, then it has to wait for until that particular event happens. And once that event happened, even that cannot be directly running, because it has to check from the scheduler that is it the task that is at the correct priority to run at the moment, or some high priority task is already being there into this particular action. Okay, getting this point? I think these particular task transition states are important from this particular perspective. And let me tell you in advance that this, whatever the application that you are supposed to write in a multitask way, or when you want to have a control over the application, then the programming, when you're making a program, or when you're writing a program for a for having the control over the time, then you really cannot do that unless you have the very own insights of this particular process states. Because whenever you want to have a synchronization, or whenever you want to have an interrupt ability to be expected written into your application with the operating system, you really cannot get to do that very efficiently. And if you really get to know this particular state transition diagram very well, then there won't be any issues on it. Getting my point? So this particular diagram is a general diagram for operating system. For MuCOS2, we have one special diagram which MuCOS2 is being added with. Okay, and that diagram is very much resembling or similar to this. So this is a general flow that we have for this particular diagram. Okay. Then, as I was talking about, there happens to be a memory block. There happens to be a memory area whose attributes are basically expected to be taken up, for controlling the parameters. Okay, or controlling that particular execution processes. So that particular process control block happens to be in this way. You can have the states of the process. Okay, the encoding of these particular states, which state the process is undergoing, that encoding has to be there, and this particular process state field of that particular process control block would maintain that particular encoding of the state. The process number, that's we call as a process ID, PID. So that particular process ID would be there as one of the attributes of it. Then program counter, the value of that program counter would always be there into it. The different registers which are being there, that also will be there in a process control block. You have got memory limits, which is being defined for that particular process, and list of the open files and all that will be there. This is a general flow where the process control blocks would have with it. Okay, in respect to the MuCOS2, we'll see each and every field in detail, because MuCOS2 scheduler works on this particular task control block in a manner of the high priority and ready to run is the task that must be running. I repeat, high priority and ready to run is the task that must be running at any point of time. Means if a particular task is running, then the system should have a valid reason to understand that why this particular task is running, because that task was highest priority task among a number of tasks when it got scheduled. Okay, it was got highest priority task and which was also ready one. So ready and, so this and what I'm talking about is a logical ending. So ready and highest priority. Okay, so likewise you are supposed to make the synchronization, or supposed to make the uh, scheduler to be written at your own also in many of the instances when you are making use of this OS. So in the discussion of MuCOS 2 will be very specific onto it, because the scheduler takes this data structure called process control block in order to decide whether that task could be scheduled or not. And let me tell you that number of tasks would have number of process control blocks, or number of processes will have number of process control blocks. Okay, if in application I have got n processes running, then I should have n process control blocks, which scheduler should be given an access for the scheduling purpose. And you can see that the information that is being given here is information associated with each process is called as a task control block. Then process states, maybe like running state, waiting state, dormant state, new state, created or terminated. So all these states has to be recorded here as in process state in an encoded fashion. Okay. Then we have a program counter. Then we have got a program counter where location of the instructions to the next execute, that it keeps the track of execution. As we know, CPU registers contents of all process centric registers, that is register file, what is being required for that particular process, that would be given. So CPU scheduling information, that is priorities, scheduling queue pointers and all that, that would be required. Again, memory management information, that is memory allotted to the processes are expected to be there in memory limits and all that. The page size, number of pages and all that would be used for this particular process when it's executing. Then accounting information, that how much percentage of CPU is used by this particular task, what is the clock time when this particular task is being started, what was the clock time, what is the elapsed time of that particular clock when this particular process is about to be terminated, because this can be start and time limits and all that, that is to be there. And this is what we call as an accounting or statistical information related to task. Okay, if you run the profiler even in your system, when you run to profiler, you can definitely get to know a specific task, the utilization of the CPU. And utilization of the CPU is always being computed based on the querying for the statistical information that the task control or process control block would have with it. Okay, I'm talking about internal, how exactly the application called profiler would be able to give you the percentage utilization of the memory as well as CPU for that particular task which is running out. Okay, then IO status information, that would be there, like IO devices which are being allotted to the processes, list of open files and all that is being there with it. Okay, then very interesting thing that we need to understand, how does the CPU switch from one process to other process? And I really want at this moment that you can refer this particular diagram for a minute or two, and the way in which it is being given from left to right, you please read this particular diagram so that I don't need to narrate much onto it. The CPU switches, that is from process 0 to process 1. What are the different activities that would take up from process 0 to process 1? Okay. So if you see, it is being clearly written or given in a diagrammatic way that when process 0 and process 1, when switches from process 0 to process 1, you can see that process 0 is executing, and let's say you have got some interrupt or some system call that happens. So it has to save the state into process control block of 0, which is related to process 0. Then after doing that, it has to reload the state from process control block 1. States in a sense what is the execution state of that process control block, what is the execution state of this particular process P1, and upon finding out its legal way, then it can give the call, or it can start executing. Till that, process P1 would be an idle one, so the process P1 would be executing, and after this particular, against the interrupt system call that comes up, and the process P0 has to be executed. Again, you can see that it has to save the state into the this particular process control block, the current state that has to be saved into process control block, whether it has been waited, whether it has been terminated. If it is being waited, then it should be known to the scheduler that it has been waited, it is not being terminated. So waited for what? Waited for some event. So once that event occur, it would be there into the ready state. So that kind of information is also expected to be known to the scheduler, right? So that is what, once some system call or interrupt occurs, it would again need to save the state into the process control block 1. And again, this process control block 1, again, it has to reload the state from process control block 0 and then starts executing of it. If you look at this particular diagram, then whatever the idle time that is being shown, no, from this execution, this process to this process, we have got these two idle times. These idle times means that no process is actually running. These idle times means no process is actually running. So whatever the amount of time that, whatever the activities those are being there into these idle times are the housekeeping activities in order to manage this particular task. And whatever what we are talking about is referred to be as a context switch. Context storing and context restoring. That's what it's a save and reload. It's called like that. Okay, when these dots are there are so many activities which are expected to be there again into it. It's not only the state that is to be saved. It's even the context also expected to be stored. So when we know this, this idle time, we have got the fair chance to understand, as it does not contribute to the functionality, as it does not contribute to the execution profile of that particular processes. Shouldn't this particular time should be as small as possible? Overhead time has to be as small as possible. And that is what the reason that when these context switches are being there, when these context switches are expected to be written, they are always written into the assembly language by making use of the most faster way of operation through register files. That is through CPU registers. And that is what even in the porting also we tried and understood the same thing, that being this as an overhead time, we have to do this particular context switches very fast. If most of the time is being there into this particular operation, then the percentage utilization of the process for the CPU, that would drop down. And that will not be referred to be as an efficient operating system usage. And that is what I insist all the time, is whenever we should know well in advance what are the contexts and all these things are being there. If we know very deterministically the context and everything, we can allocate the memory and we can allocate the register so that we get to know that what are the operation that it would be doing and how much time it will be there for it. It's as simple as that. When it would be possible, when this idle time would be constant, if we are known with the context. If you're not known with the context, we cannot say this is always going to be a variable one. And when this is a variable one, you cannot have an estimate of that particular execution profile. And when you cannot have an estimate of the execution profile, you cannot say that you are designing a system which are deterministic in nature. So if you're not designing a system which are deterministic in nature, that systems are not referred as in real-time systems. That is what the general purpose operating system, we need to take up so many things from this general purpose operating system, that the idle time, which is the context switch time, has to be less as possible as it. And all the efforts that is what the underlying processor should have a register file. Underlying architecture should have very large file of it, so that this can be made very fast. Getting my point? So these faster operations are always being beneficial when you are having a very strong support of the underlying architecture. And that is again, I'm referring it to the port file called as an os underscore cpu underscore a.s. This particular file is completely written based on this particular phenomenon. Okay, fine. So we understand the CPU switch from one process to other process. This context switches and all what I discuss at the moment is being written there, but we'll continue it in the next time, as I saw the hand raised from Devdutt. So I definitely need to stop at this particular point of it. Okay. So further, what we are supposed to discuss is context switch, different representation that we have in the different operating systems, like the Linux operating system, what all the different process schedulings is behind, then representation of the process scheduling, then what are the different operations those normally happens into the process, like creation, termination, and all that. And then we'll see that the difference between parent thread, child process, how does exactly it typically gets represented into the Linux kind of operating system. And then we'll see how does the different system calls are being used for these particular processes. And then we can say that we understood fairly the task control management or task management aspect of operating system. Okay. And as I said you that these are the books which is extremely helpful. These are my favorite books, which I always refer it for this study of operating systems. Okay. I'll pass on this book, even the soft copy, I'll pass on this. Okay. So we'll keep on discussing this. Most probably till tonight, I'll try and make this video of this particular session. Okay. Fine. So let's okay, please fill out the attendance in this Google form so that Nikhilesh, Saurabh have done it. Ashutosh Kamble has done it. Ajit Sambre has done it. Samta has done it. Abhijit has done it. Aditya, Anand, Ashwini, Tejas, Tanmay, Harshvardhan, Sumedh, Rohan has done it. Sunaina has done it. Hussein has done it. Bhagwat Akash has done it. Viraj has done it. Arya done it. Shreyas done. Nitin has done it. Okay, so if you have done it, then let me end this particular session.